So today we will get started with the notion of function space. Function spaces are infinite dimensional linear vector spaces, and the particular kind of function space that we will be interested in is called the Hilbert space. Okay? So let me start with the basics of function space. This module will sort of get you up and running about what a function space really is in terms of a very simple example, which we adapt from Shankar's textbook on quantum mechanics. So the reference to whatever I'm going to be talking about now is Shankar's textbook on quantum mechanics. Okay, so let us start by asking a very simple question. So suppose if you have a piece of string, right? And let us say that I have my axis like this, and then you have a piece of string with some kind of a displacement. Okay. All right. So this displacement I will call some f. Okay. Now suppose if I were to tell a friend of mine exactly what the shape of the string is, mathematically what I would do is I would tell him the displacement at every single point. Excuse me. Displacement at every single point, right? Over what is the value of the string displacement at this point, this point, this point, this point, this point, so on and so forth, right? So let us say that initially I tell him the displacement of the string at, let us say, 5 points, okay? Now this is a very crude approximation to the string, and my friend won't be able to reconstruct this string based on what I've told him, but let us assume that this is what I initially tell him. Okay, so I tell him f of x1, f of x2, f of x3, f of x4, and f of x5. Okay, these are the numbers I give him. The displacement is 2 centimeters at x1, 5 centimeters at x2, and 13 centimeters at x3, 3 centimeters at x4, and 1 centimeter at x5, whatever it is, right? Of course, he won't be able to reconstruct the string with this crude data, but let us see how much we can push this forward. Now, in some crude sense, I can construct a vector in a 5-dimensional linear vector space whose components are these displacements. Okay, why not? Like so. Yeah. Okay. So I will also label it F5 because this is a 5-dimensional vector. And the components of this vector are the displacements at these 5 different points that I have given it. Now, in what sense can I write this as a component of a vector? Is there a basis in this 5-dimensional space? Yes, of course, I can write down a basis in this 5-dimensional space. My x1 would be 1 with 4 zeros. My x2 would be 0, 1, 0, 0, 0, and so on and so forth, right? My x3, I can think of it as 0, 0, 1, 0, 0. x4 and x5 similarly. I will simply write this down for completeness sake, 0, 0, 0, 1, 0. And my x5 would be, okay, these are my 5 basis vectors in this 5-dimensional space in which I've written down an arbitrary vector f5 whose components I've chosen to be the displacements that are given to me, the data that is given to me. Viewed in this way, now I can think of this f5 as a legitimate vector by writing this as I equals 1 to 5 f of xi, xi, right? This is exactly how you write a vector. Remember that if you have any vector in some basis space that is spanned by some vectors ei, you write this as some alpha I, ei, where alpha I are the components of the vector. Similarly, I'm writing this f5 as the summation or a linear combination of the basis vectors xi. Okay. Now, suppose if I want, so this is All perfectly fine. There is nothing very troubling about this. But of course, this experiment is very dissatisfactory because it's not very satisfactory because my friend will not be able to reconstruct this string. In order for him or her to be able to reconstruct the string, I need to be able to give more and more and more and more points. Okay. And the only way in which the string can be reconstructed completely is if I give him or her an infinite number of points. But sticking with this 5-dimensional linear vector space, remember that my basis vectors satisfy orthogonality and completeness. It's simply the unit matrix, as you can clearly verify. So this is all fine. So then, suppose if my friend were to reconstruct the entire string and I were to give her the entire bunch of data, an infinite number of data, then how does this generalize? The question is, how does this generalize? Can I write a very straightforward infinite dimensional vector, which I will call f, with infinite number of components? And should I write down an infinite number of basis vectors as column matrices in this form? Well, obviously, writing down infinite number of column matrices is impractical, as you can easily understand, right? So I need to have a convenient way in which I represent an infinite dimensional basis vector and an infinite dimensional vector. And I need to understand how the notion of orthonormality, which is xi xj equals delta ij, and the notion of completeness, which is sum over I xi equal to 1, how do these things generalize to infinite dimensions? This is what we want to understand, right? So how would you go about answering this question? So to answer this question, so let us first also recapitulate in this 5-dimensional space. In addition to these two, we also have the notion of inner product, right? Inner product in this space. Suppose if I have two functions, the inner product of f of n, g of n is simply equal to I equals 1 to 5 of fn, rather fn of x, gn of xi, right? This is exactly how. Of course, if I have complex valued functions, it will be fn star xi, gn xi. I also want to know how this particular notion generalizes, the notion of dot product or inner product of two vectors, right? So let us try to write down the corresponding formulas in the infinite dimensional linear vector space scenario. Okay. So I want to be able to, let us take this inner product to begin with. So let us take fn gn equals sum over I equals 1 to 5 fn of xi, gn of xi. Okay. Now I want to blindly generalize this to infinite dimensions. Okay. And also the norm of the vector, excuse me, is defined as I equals 1 to 5 fn of xi quantity squared. Okay. Now notice that if I have any function and if I were to go from 1 to infinity, I'd be adding an infinite number of components. Okay. And if this was a complex valued function, the only thing that will change is fn inner product would be fn star fn, which is manifestly a positive quantity. If I add up an infinite number of positive quantities, at some point I'm going to get into trouble because the sum is going to diverge, right? For any reasonable function. Of course, you can think of functions that are 0 for all x beyond a certain point, and those functions would be okay, but those would be artificial. The most general kind of functions that you can think of all have non-zero values of x. They can be decreasing values of x. The function can not behave very badly, and that is totally fine. But there could be functions that do behave badly, and then adding more and more components will simply cause this to diverge. So we should first be able to redefine the notion of inner product in such a fashion that the sum does not diverge. Okay, the way to do this is one way in which one can motivate this, is redefine inner product fn as sum over I. In this case, let us say sum I equal to 1 to n, where n is a very large number. I'm going to take the limit n goes to infinity. Fn of xi, gn of xi, and I will weight this by a factor equal to, let us say, if I stick with this example of the string, and let us say that the string length in this case is something like L, and I'm choosing n points in between to describe the string. I will weight this by a factor of delta, where this delta is some L over n. Okay, should ideally be n plus 1 because I'm going from 0 to n. So basically, all I'm saying is instead of choosing 5 points, now I'm choosing n points to describe this string, right? Where there is not five crosses, I have now n different crosses, where n is a very, very large number. So I want to understand the string problem in the limit that I take an infinite number of points to describe the positions of the various parts of the string. Okay. So I will redefine my inner product with this particular uh, um, in this particular way. Now you might ask, how can you possibly redefine the inner product? Inner product is given to you. No, it is not. Inner product is a choice. Okay, so inner product should conform to certain rules. Okay, it has to obey linearity, which is the most important rule, and it has to the complex conjugate. So if these were complex valued functions, excuse me, fg should be equal to gf star, right? And if I consider something like f alpha g, this should be alpha fg. And if I consider alpha fg, this should be alpha star fg. And linearity, which is f some alpha g plus beta h, should be alpha fg plus beta fh. This is the notion of linearity. As long as the inner product that I define in the linear vector space obeys these simple rules, the definition is fine. For example, in the space of matrices, we saw a tutorial problem in which I can define the inner product in the space of, let us say, 2 by 2 or 3 by 3 matrices as trace of A dagger B. Right? That is a very valid notion of inner product in that particular space. So I will redefine this inner product in this particular fashion, Fn Gn times delta, where delta is simply the length of the string divided by the number of points I take. And in the limit n goes to infinity, so I equals 1 to n, Fn of xi, Gn of xi, L over n. In the limit n goes to infinity, what happens if I have an infinite number of points? Then a sum is not a valid mathematical operation anymore. The sum should be ideally replaced by a continuous integral over the entire one-dimensional space. So the sum I equals 1 to n goes as transforms into an integral. Okay, the integral can be from x is equal to 0 to x is equal to L in this case. Now Fn of xi simply becomes some function of x, because there is no I anymore, because there is an infinite number of i's. So there is no point keeping track of them. This is again g of x. And what is L divided by n? L divided by n, the delta, the displacement, can be written in the limit that n goes to infinity. Delta, which is L over n, becomes an infinitesimal displacement dx. Okay, so the notion of inner product in a one-dimensional function space is redefined as f g equals integral f of x, g of x, dx between 0 to L. Now, why 0 to L? Because we chose an example where the string is between 0 to L, but in quantum mechanics, we will not necessarily confine ourselves to 0 to L. In fact, the most general Hilbert space is one in which we go from minus infinity to infinity. So the limits depend on your problem, okay? So the limits of integration depend on the problem at hand. In general, it goes from minus infinity to infinity. But suppose if you have a particle in a box kind of scenario where the wave function is 0 beyond certain points, you can restrict your inner product between the points where the wave function is non-zero. Okay. Now, if these were complex valued functions, the inner product would generalize to, as you can easily guess, it will go to. Now I'll write minus infinity to infinity from now on because we will move away from the string example. F star of x, g of x, dx. Okay. So this would be my definition of norm in the function space. With this definition of norm, suppose if I take the inner product of a function with, not norm, inner product, the definition of norm in this space would be ff would be obviously minus infinity to infinity f star of x, f of x dx, which is minus infinity to infinity f of x squared dx. Okay. Now, what is this? This is basically the component of f at every single point x, the mod square of that component, and we are adding the mod square of the component. So this is basically the generalization of the length of a vector to infinite dimensions. And we want to restrict to those functions such that restrict to those functions which obey minus infinity to infinity mod f squared. The length of this vector should not blow up. It should be less than infinity. Okay. If there are functions that do not obey, then we don't consider them to be legitimate functions in the Hilbert space or linear vector space that we are operating in. Okay. So this is an important point to understand. And functions that obey this condition that the length square does not diverge, there's a special name for them. They are called square integrable functions. So in quantum mechanics, we always deal with square integrable functions. Okay. Now this space that we are looking at, an infinite dimensional linear vector space in which the norm is, or the inner product is defined in this particular fashion, has a special name. The space is called L2 minus infinity to infinity. Now, what is minus infinity to infinity? Well, that is the extent of the Hilbert space that we are looking at. That is the extent of the linear vector space. It is valid from x is equal to minus infinity to infinity. What is this L2? Well, the L2 has to do with the fact that we are using the definition of what is called a Euclidean norm, right? So suppose if I define the length of a vector x, so length of a vector x as square root of all the components squared, x1 square, x2 square plus x3 square plus blah, 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 right? So this is x1 square plus x2 square to the power of 1/2. Okay. So there is I'm taking the square of each individual component and then taking the square root of the entire sum. I can also redefine my, so this is where the 2 comes from because of the square and the 1/2 factor over here. Suppose if I define my length of the vector to be something like x1 to the power p plus x2 to the power p plus so on and so forth, and take the power 1 over p. Okay, and I redefine my length of the vector to be this quantity instead of the Euclidean distance that I've defined before, then I'd be operating in something called the LP space. Okay, in quantum mechanics, we will stick with L2 space, and this will be, so this is the regime of quantum mechanics. Quantum mechanics will always operate in the L2 space, but there are other mathematical spaces also. Okay, there are spaces, for example, that do not admit a norm. Okay, it is certainly possible, but you can generally be satisfied that if you are dealing with square integrable functions, then the inner product defined in this fashion between two different vectors is also a converging quantity. It will also not diverge. Okay, we will not prove this, but we'll simply take it for granted. If I live in a square integrable functions in which the length of every vector is finite, in the sense that integral f of x squared dx is less than infinity, then the inner product of two functions in this vector space is also finite. Okay, we will take this without proof. In quantum mechanics, we deal with a very particular kind of linear vector space called the Hilbert space. Okay, now I will not go into the technical definitions of Hilbert space, which will take me 2 to 3 lectures, but we will simply understand for our purposes a Hilbert space as an infinite dimensional. Now it can be finite dimensional also, but in finite dimensional Hilbert spaces, there is no real subtleties. In infinite dimensions, there are subtleties, as you would soon see. This would be an infinite dimensional linear vector space, which is complete as a metric space and is also an inner product space. Okay, now there is a bunch of technical words there. I will simply qualitatively explain what this means, and we will move on. An inner product space means that this is a linear vector space in which I can define the notion of inner product of two vectors. Okay. Now, complete as a metric space. Now, completeness here means something very different from completeness of basis vectors. Okay, that is not what this means. Completeness simply means that, suppose if I take a sequence of functions or sequence of numbers, as the case may be, then there are sequences called Cauchy sequences. Cauchy sequences are those in which the distance between 2 points keeps on decreasing. Okay. So if every such sequence in my Hilbert space is also a converging sequence, which is a necessary condition if I am to have square integrable functions, then such a metric space is called a Hilbert space. Okay. Sorry, not a Hilbert space, a complete vector space. A complete vector space is one in which every Cauchy sequence necessarily converges. Okay, this is a technical definition, and I'm sure you will learn more about this in your mathematical physics course. So for our purposes, we will simply use the definition of Hilbert space as one in which it's an infinite dimensional linear vector space in which the norm is defined in the manner that was defined previously. Okay. All right, so with this definition in place, we want to move ahead and define the notion of orthonormality of basis vectors and how to project out components of this infinite dimensional vector. Okay, so we will turn to that question now. Okay, so let us move on. So let me draw a line here. Excuse me. Okay. So remember or recap that if I have a finite dimensional linear vector space in which my basis vectors are EI, right? Now I have my orthonormality relation EI EJ equals delta IJ, I have my completeness of basis vectors, which is ei equals 1. And I know the projection of every vector. Suppose if I have this projection operator along the direction ei, and if I multiply this on any alpha, then this gives me the component of alpha that lies along the direction ei. So this is some alpha I ei. Okay, so this is how I work out the components of the vector along different directions. So how do these notions generalize to infinite dimensions? So my basis in infinite dimensions is X. We are looking at the X space. We'll also look at other spaces later, but for now, let us restrict to X space, one dimension. Okay. Now, I should also have the notion of completeness, but instead of, let us say, sum over xi equals 1, I cannot have xi because there is no points as we've discussed, and there is no sum, there is an integral. So completeness, it's not hard to see that the notion of completeness should generalize to integral dx x equals 1. Okay. In fact, I can just write down 1. This should be the notion of completeness. This is not hard to see. This is how, for example, this would generalize. Yes. Okay. Now, what about orthonormality? Well, if I have two different bases vectors, x and x prime, let us say the overlap of x and x prime, the orthonormality simply means that if you take the overlap of two different basis vectors, it should be 0. And if you take the overlap of same basis vector, it should be 1. But in a function space, you would actually see that this is actually a slightly complicated thing to define. So I should define my overlap of two different basis vectors, which is a continuous basis vector. Overlap, this should be 0. But what if I take the overlap at the exact same point? Can I get 1? You will actually see that this is not very straightforward to define. What is xx? Is it equal to 1? Okay, let us work this out. Let us work this out by understanding what is the projection operator. The projection operator is basically xx, right? Suppose if I have the projection operator is xx, and if I operate it on any vector, I should be able to get the component of that particular vector. Okay. Now the completeness relation tells me that if I add up all such projections, I get 1, right? This is equal to 1. All right. So take this and multiply the above equation by x. Let me use a different x here. So let me call this x prime, x prime, x prime. This is a dummy index that is integrated over. So it doesn't matter if I call it x prime or x. Multiply by x, bra x on the left, and some vector, some arbitrary vector, f on the right. Okay. Now limits is whatever they are. So I'll put some limits a to b. A can be minus infinity, b can be infinity, a can be 2 and b can be 45 depending on what the problem is. Okay. So this is a, b. If I multiply by x on the left, I get x prime. This is the quantity I want to understand. What is the overlap of two different basis functions? And this is x prime f dx prime. And this is equal to xf. Now this quantity xf is easy enough to understand. This is basically the projection of the vector f along the direction x. So this simply gives me the value of the function at the point x, right? So just like if you go back and look at, for example, this one, right? So if you look at this guy, if you project out the component x3, if I take the inner product of this with x3, I would get f of x3, right? So it's exact same thing. Similarly, this guy is f of x prime, right? So that much is clear, okay? So now this equation becomes a to b x prime f of x prime dx prime equal to f of x. Now let us stare at this equation for just a second, right? So I'm integrating a function over x and I'm multiplying it by some quantity which is a function of, so let us call this quantity some function of both x and x prime, okay? So if I rewrite this equation, I get this function which is a function of both x and x prime multiplied by f of x prime dx prime gives me f of x, okay? So let us say that in my one-dimensional space, okay, so let us say that this is my a and this is my b, and let us say that this is my x prime and this is my x, whatever it is. So there is an infinite number of points. I'm choosing two different points, x prime and x. Now this is the value. So f of x prime is the value of f at the point x prime, okay, and f of x is the value of the vector f at the point x. So look at this integral equation. This is rather strange because I'm multiplying f of x prime, the value of x prime, by some function such that this gives me the value at f of x. The only way I can actually define this function in this particular fashion is by claiming that this function delta of x and x prime is a very strange function, which is the, if you want a generalization of the canonical delta function that we defined, it should be a function such that it should be 0 if x prime is not equal to x, and it should be equal to 1 if x prime equal to x, okay? In other words, I will write this delta of x prime, delta of x prime, x comma x prime, it should be a function such that it should project out the value of the function at the point x, okay? So which means the delta of x comma x prime should know both about x and x prime, and it should be only a function of the difference x minus x prime, because it should be equal to 0 if x is not equal to x prime and 1 if x equal to x prime. So if I plot a function like that, I will get something very weird. Let us say that this is my delta of x comma x prime against x. And this function should be such that it should be 0 everywhere except at the point where x becomes x prime. Okay, so this is not a very good plot, but it should be an infinite peak at the point x equal to x prime. Okay, this function is called the Dirac Delta function. I'm sure you have seen the Dirac Delta function in other places in your physics studies. Dirac Delta function. The Dirac Delta function has the property that the area under the curve, if I go from minus infinity to infinity, delta of x dx, this is equal to 1. Okay, and it also has the property that it serves as a very nice projection operator, or not a projection operator, it serves as a nice way to pick out the components. So delta of x minus a f of x dx would pick out the value of the function at the point a. Okay, so if you think about it, that is what a projection operator does. It picks out the value of the vector along some particular basis ei. So the overlap of the basis functions x prime in the case of continuous basis, is equal to delta x minus x prime. Okay, so this is not just 1 or 0, because delta function is not equal to 1 when x is equal to x prime and 0 when x is not equal to x prime. Well, it's certainly 0 when x is not equal to x prime, but at the point x equal to x prime, it is an infinite peak. So we can only truly understand this under an integral symbol. Okay, this unless I write it under an integral symbol, the delta function and this overlap is not very particularly well defined. So we say that this basis is delta function normalized. Okay, so this is the generalization of EIEJ equals delta IJ. But as you can see, it is not a straightforward generalization. Okay, in other words, I cannot simply write x prime equal to 1 if x is equal to x prime and 0 if x is not equal to x prime. It is a slightly more complicated way of writing the orthonormality, even though the completeness relation is rather straightforward. Okay, so there is one way to understand the delta function. One way to understand this delta function, which is not truly a function at all, it's actually a functional. It's a functional because if I convolute this delta function with some function f of x, I get the value of the function at the point where the delta function is non-zero. But one way to understand the delta function in terms of functions is to view it as a limit of some function. So delta function can be viewed as the limit of other functions. Excuse me. For example, if you take a Gaussian function, as you know, is, let us call this some g of x, some normalization e to the minus, let us say x minus a the whole square divided by some delta square or something like this. Okay, so this is an example of a Gaussian function. So what does this Gaussian function look like? So if you plot this Gaussian function, you would look something like this. Okay, so this would be the point x is equal to a, right? And it is symmetric about the point x is equal to a. Now it has a width delta, and if you choose this normalization n properly, choose n such that minus infinity to infinity g of x dx equal to 1. You can always do that. Okay, such that the area under the curve is 1. So this is basically normalizing the function. Now imagine that I keep shrinking this Gaussian function more and more and more. Okay, so I keep decreasing this delta. So if I shrink this function, if I want to keep the area under the curve still 1, I have to increase the height of this function. So I can think of this as going to something like this, something like this, something like this, and so on and so forth, right? In the limit that delta goes to 0, I can view this as the Dirac delta function. So in the limit delta goes to 0, g of x in the limit delta goes to 0 can be thought of as the delta function. Okay, that is one way in which you can visualize this delta function. Otherwise, it's rather hard to see how this delta function behaves because it is not a conventional function. It is certainly not continuous, right? Because it's an infinite peak at one point and 0 everywhere else. So that is not your example of a very nice continuous function. Surprisingly, it is differentiable. So it is actually a very weird function. Okay, so for this module, we will stop here. Basically, our job was to introduce the notion of function spaces and how you would set up the basis vectors in a function space and how you would expand other vectors. So the expansion of other vectors is now hopefully clear. I can expand a vector f as, I can write down, I can simply insert the completeness relation. This is just one, right? So I can write this as this x hits on this f on the left. So I can write this as xf dx, and xf, the projection of x, the projection of f along the direction x is simply the value of the function vector at that particular point x. So I can write this as integral f of x dx. Okay, so this is the expansion of the function in an infinite dimensional linear vector space, and the basis vectors x satisfy the completeness relation x equals 1, and the delta function normalized. Okay, so this is the important lesson for this module, and we will continue the next module by talking about the position operators in general and how position and momentum operators can be defined in this particular space.